So how do we determine behavior of solutions of a second order linear homogeneous differential equation with constant coefficients? Right. So recall that in order to solve this differential equation, we need to write down the corresponding characteristic equation first, and then we look at the solutions of the characteristic equation. So the characteristic equation is r squared plus ar plus b is 0, and then we solve it. We find the zeros or the roots of the characteristic equation, r1 and r2, and they tell us what the general solution of the differential equation is. Now, essentially, there are two different cases. So the roots of the characteristic equation can be either real or complex. So the roots are real if and only if the discriminant is non-negative. So if the discriminant is not non-negative, discriminant of the quadratic equation is a squared minus 4b. If it is non-negative, then the roots are real. So, and in this case, if the roots are real, then the solution is going to have e to the r1t and e to the r2t, where r1 and r2 are the roots. So, what does it mean? The important part is whether the roots are positive or negative, because if we have a positive number here, then the exponential function, it approaches plus minus infinity when t goes to infinity, or 0 when t goes to negative infinity. So if this number here is negative, then the exponential function approaches 0 when t goes to infinity, and plus minus infinity when t goes to negative infinity. Right? So in other words, we need to determine whether r1 and r2 are positive or negative. Well, how do we do this? So recall that in any case, the product of the two roots, r1 times r2, is b. And the sum of the two roots, r1 plus r2, is minus a. Well, so in this case, when the discriminant is non-negative, well, let's think of b. So b can be either positive or negative, right? So b could be, well, let me look at the case when b is negative first. If b is negative, it means that one root is positive, another one is negative, because the product of two numbers is negative if and only if one of them is positive and the other one is negative. Right? So it means that r1 is, say, negative and r2 is positive. Well, but then the general solution looks like a combination of an exponential function with a negative exponent and the positive exponent. But then, of course, it means that most solutions approach plus minus infinity when t goes to infinity. So in this case, the picture of solutions, so solutions could be, say, we could have solutions that approach infinity on both sides. We could have solutions that approach, say, minus infinity on the left and plus infinity on the right, and we could have solutions that approach, I don't know, negative infinity on both sides, and so on. But it's always plus minus infinity. Well, or b could be positive. If b is positive, it means that the roots are both of the same sign, so either two positive or two negative. But of course, if the two roots are positive, well, let me write, so either r1 is positive and r2 is positive, or r1 is negative and r2 is negative. So either both positive or both negative. So in this case, we should look at the sign of a. So now we should either, well, either A is going to be positive or A is going to be negative. So if A is positive, so we know that the two roots are of the same sign, either both positive or both negative. If A is positive, it means that the sum of the two roots is negative. And the two roots themselves are either both positive or both negative. But if the sum is negative, then of course both of them have to be negative, because if both of them were positive, then the sum would be positive too. So both roots are negative. In this case, R1 is negative, R2 is negative. So both solutions, e to the R1t and e to the R2t, approach 0 when t goes to infinity, and approach plus minus infinity when t goes to negative infinity. So the picture of solutions looks like this. So all of them approach 0. So it could be something like this, something like this, or maybe something like this. But all of them are going to approach 0 when t goes to infinity. So when A is negative here, then by the same logic, the sum of the two roots is positive. So since the roots have the same sign, it means that both of them are positive. But in that case, of course, we are going to see essentially the same pictures here, only it's reversed. So now the limit of all solutions as t goes to positive infinity is going to be plus minus infinity, but as t goes to negative infinity is going to be 0. So solutions will be probably look like this. So they become 0 at negative infinity, or could be something like this, or could be probably something like this. But at negative infinity, they all approach 0. Now, this is all the cases that we can have with two real roots. I did not explain the case of a repeated real root. But basically, it's the same, only when the root is repeated, we cannot have this, because this is the case when the two roots have opposite signs, so they cannot be equal. But these two cases, they actually cover the situation when R1 equals R2. It's just that if R1 equals R2, there will be slightly different solution. It's going to be a combination of e to the RT and t times e to the RT. But the general picture is very similar. You can't really tell from the plot whether the roots are repeated or the roots are not repeated. So a completely different alternative is when the discriminant of the quadratic equation is negative. Right? So if a squared minus 4b is negative, then we are going to have complex solutions, right? And then the complex solutions, as I explained in the lecture, they can be well, instead of writing it as e to the R1t and e to the R2t, we can write it as e to the power lambda t times a combination, say c1 cosine mu t plus c2 sine mu t. So in this case, R1 is lambda plus I mu, and R2 is lambda minus I mu. Well, but then notice that R1 plus R2 is 2 lambda, and at the same time it's minus A. So in other words, lambda equals minus A over 2. And now the important parameter here is lambda, because this is a trigonometric function, so it just oscillates between two values, so that there is not much of a complicated behavior here. So we really have three sub cases. So either lambda can be positive, and lambda is positive whenever a is negative. And if lambda is positive, then here we have an exponential function with a positive exponent, so it is an increasing exponential function, but multiplied by an oscillating function, we are going to get oscillations of magnitude that is increasing exponentially with every next iteration. So the picture is something like this. So it's going to be bigger and bigger oscillations. Well, so another case that we may have is when lambda is exactly 0, which happens when a equals 0. And if lambda is 0, then e to the 0 is just 1. And the solution is just an oscillating function. So in this case, all solutions are going to be just oscillations. So they're just going to be like this. Well, and the last case is, of course, when lambda is negative, so which happens when a is positive, and in this case, when lambda is negative, here we have e to the negative power t. When t goes to infinity, this term goes to 0, and this term is oscillating. So in other words, what we are going to see is oscillations of magnitude that is decaying to 0. So we are going to see something like this. So here oscillations are decaying. So the magnitude is decreasing as t goes to infinity. Well, but in any case, notice that what we see is that all solutions approach 0. So when do all solutions approach 0? In either this case or this case. But these two cases together, they are characterized by the fact that a is positive and b is also positive. So notice that in this case, b has to be positive because if a squared minus 4ab is negative, then a squared is a positive number. So in order for the whole thing to be negative, b has to be positive too. So probably I should mention that here b is automatically positive. So, and at the same time, in any other case, either b is negative or a is maybe negative. A maybe, yeah, negative, or I don't know, say here a is negative. Yeah, so what I want to say is that what we see is that all solutions approach 0 when t goes to infinity, if and only if both coefficients here are positive. So that's one implication. But depending on the sign of the discriminant, so when this happens, the solutions may approach 0 in a different manner. So they can either just approach 0 sort of in a straight way, or they can approach 0 in an oscillating manner.